The heaviest non-nuclear bomb ever used in combat weighs 30,000 pounds. It carries 5,300 pounds of explosive material, making up just 18% of the weapon's total weight. The rest is steel, and that's by design. These bombs are air-delivered munitions, designed to penetrate hardened underground structures before detonating. And that hardened steel casing is engineered to survive deep penetration through concrete and rock. The casing is the weapon. The explosion is secondary. Most people assume the opposite. The name suggests a massive explosion that shatters reinforced bunkers from the outside, but instead it drills in and then detonates from the inside. 3 physical properties govern bunker buster performance. The first is structure, the geometry of the casing. The second is mass, total weight at impact. The third is speed, velocity at the moment of penetration. How deep a bomb travels before stopping. The explosive charge activates after the bomb has stopped. Without penetration, the explosion does little. A narrow, elongated cylindrical body concentrates force at a single point. When force is concentrated at a narrow contact area, pressure at that point rises. High pressure against a hard surface, concrete, granite, compacted earth, allows the nose to push through material that would deflect a wider object. This is the same principle that makes a nail penetrate wood where a flat block would not. The bomb's geometry is the primary engineering constraint of the design. The nose cone at the front of the bomb is made from the hardest available steel alloy. It must survive the initial impact without deforming. If the nose deforms on contact, if it loses that point, the bomb's geometry is compromised. It will deflect, tumble, or shatter before reaching target depth. The nose is the most mathematically critical component of the system. Behind the nose is the main casing body. This is where mass is stored. The casing on the GBU-57 Massive Ordnance Penetrator is constructed from a high-density alloy designated Eglin steel, or ES1. This material is engineered to withstand the compressive stress of boring through reinforced concrete at high velocity. The casing does not contain the explosive. It transmits kinetic energy forward during penetration and protects the explosive core from detonating prematurely. The explosive charge is located inside the rear section of the casing. On the GBU-57, this charge is 5,300 pounds of high-energy explosive compound. The compounds used are selected for thermal stability. They must not detonate from the heat and shock of impact itself. Military explosives are far less sensitive than popular understanding suggests. Impact alone does not detonate them. This is an intentional property of the material. At the rear of the bomb is the fuze system. The fuze is a triggering mechanism that determines when detonation occurs. The GBU-57 uses a system designated the Large Penetrator Smart Fuse, or LPSF. Multiple fuse types are used in penetrating munitions. The first is a simple delay fuse, which waits a fixed time interval after impact before triggering. The second is a void sensing fuse, which detects changes in resistance during penetration. The third is a programmable fuse that combines both methods with microcontroller logic. The void sensing fuse detects when the bomb passes through an open chamber underground. As the bomb bores through the soil or concrete, resistance is constant. When the nose enters an open interior space, a tunnel, a chamber, a command center, resistance drops. The fuse detects this change and triggers detonation at that moment. Some versions of this fuse include a microphone that counts the number of structural layers the bomb passes through, detonating at a programmed floor number. When the bomb detonates inside an enclosed underground chamber, the explosive energy has nowhere to expand outwards. Pressure builds against all surrounding surfaces, walls buckle inward, ceilings collapse downward, equipment is destroyed by pressure, heat and structural failure, not by the initial blast itself. This internal detonation is more destructive per pound of explosive than a surface explosion, where most energy disperses into open air. At the rear of the bomb are the fins and guidance components. The GBU-57 uses grid fins, a lattice structure rather than flat planar fins. Grid fins fold flat for storage in the B-2 Spirit's internal bomb bays. When deployed, they provide aerodynamic control at near supersonic speeds during descent. A GPS receiver in the tail section guides the bomb to its aim point during the atmospheric portion of flight. Once the bomb enters the ground, GPS signals cannot penetrate earth or concrete. The fuse system switches to inertial tracking, resistance sensing, and pre-programmed logic. The engineering explains how it works. Why it had to be invented twice under emergency conditions in less than 3 weeks is something else entirely. This design lineage traces to British engineer Barnes Wallis and his work during World War II. Wallis formally proposed the earthquake bomb concept in his 1941 paper, A Note on a Method of Attacking the Axis Powers. The idea, a conventional bomb detonating on the surface, wastes most of its energy in open air. A bomb that penetrates the ground next to a hardened structure transfers shock through solid earth into the target's foundation. Shock waves travel more efficiently through dense material than through air. The target collapses from below, not from above. Wallis developed 2 weapons based on this principle. The Tallboy weighed 12,000 pounds, the Grand Slam weighed 22,000 pounds. Both featured a narrow, elongated body cast in one piece from high tensile steel, with a specially hardened steel plug machined into the nose to survive impact without deforming. Even in its early form, the casing, not the explosive, was the weapon. American engineers would rediscover this principle 5 decades later under different constraints, using different materials. The Tallboy's tail fins were mounted at a slight offset angle. This caused the bomb to spin as it fell, applying the same stabilization principle as a spinning artillery shell. The spin resisted deflection from crosswinds and improved accuracy. The bomb could exceed the speed of sound during descent when dropped from sufficient altitude. At that velocity, the hardened nose could penetrate deep into reinforced concrete or into the earth beside a fortified structure. Wallis's primary intent was not a hit. The bomb was designed to strike the ground near a target, penetrate into the subsoil, and detonate underground. The seismic shockwave would then travel through the foundation and destroy the structure from below. The British called this the camouflage effect, a buried explosion that creates a cavern into which the structure above collapses. This concept proved effective against hardened German U-boat pens and V-weapon facilities during the war. American engineers observed the results. Then, once nuclear weapons became available, investment in conventional penetrating munitions stopped for 45 years. That gap had consequences. When the next war came, the US military discovered it had given up a capability it needed back. It had 2 weeks to rebuild it from scratch. If you want to keep following stories like this one, where the engineering history and the current headlines connect, subscribing keeps more of it coming your way. The next major development came under wartime pressure. In early February 1991, US planners in Operation Desert Storm concluded that existing munitions could not penetrate Iraq's deepest hardened command bunkers. Engineer Al Wymotz at Eglin Air Force Base designed a solution. Material was the insight. Artillery barrels are manufactured from hardened steel alloys to withstand repeated internal blast loading. Surplus 8-inch howitzer barrels from decommissioned M110 artillery pieces were available in storage. A howitzer barrel machined to accept a guidance system and explosive charge was geometrically suitable. Long, narrow, dense, and made from the correct grade of steel. Wymotz sketched the initial design. The first 2 warheads were manufactured, loaded with explosive, and X-rayed for quality verification within 72 hours of the design being approved on February 14th. The weapon was designated GBU-28. From project approval to first combat drop, under 2 weeks. In testing at Tonopah Range on February 24th, the bomb penetrated to a depth exceeding 100 feet in desert terrain. 4 days later, it was used operationally. A later sled test fired a GBU-28 variant against a reinforced concrete array 22 feet thick. The bomb passed through the stack and continued downrange for roughly half a mile. The GBU-28 is capable of penetrating over 160 feet of earth, or 16 feet of solid concrete. The GBU-28 answered one question and raised a larger one. If a 2-week improvisation built from surplus howitzer steel could achieve this penetration, how deep could a purpose-engineered system go? The answer required another decade of work and a new threat, and that threat was being built underground beneath a mountain on the other side of the world. In 2003, post-war analysis of bunker strikes in Iraq revealed that even the GBU-28s had not penetrated deeply enough against certain targets. The Defense Threat Reduction Agency, or DTRA, initiated the Hard Target Defeat Program. In November 2004, the Air Force Research Laboratory awarded Boeing a $20 million indefinite delivery contract for the development of a weapon capable of destroying hardened facilities buried deeper than any existing munition could reach. In 2009, US intelligence revealed that Iran had been constructing a uranium enrichment facility at Fordow, buried beneath a mountain near Qom. The facility was estimated to sit 80 to 90 meters underground, beneath solid rock. DTRA analysts began studying the site. 2 analysts in particular monitored the facility from that year forward, tracking the ventilation shafts, exhaust systems, electrical infrastructure, and every piece of equipment entering or leaving the site. Chairman of the Joint Chiefs of Staff, General Dan Kane, said, "These 2 analysts literally dreamed about this target at night when they slept." The weapon they were helping to design was the GBU-57 A/B Massive Ordnance Penetrator. The GBU-57 is 20.5 feet long, it weighs 30,000 pounds, the weight of a loaded city transit bus. The casing is Eglin steel ES1 alloy, the explosive payload is 5,300 pounds, and it's guided by GPS to its aim point and carries a void-sensing smart fuse system. It's delivered by the B-2 Spirit stealth bomber. No other aircraft in the US inventory is operationally certified to carry it. No Allied aircraft can carry it. Trevor Ball, a former US Army Explosives Ordnance Disposal Technician and Associate Researcher at Armament Research Services, described the delivery constraint. The weapon, the bomber, and the avionics integration form a single, inseparable system. There is no way to transfer this capability to an Allied Air Force. The unclassified penetration specification for the GBU-57 is 60 meters of earth or 18 meters of reinforced concrete. Fordow sits 80 to 90 meters underground. The gap between specification and target depth shaped the operational plan for what came next, because closing that gap required a workaround, and that workaround was either a masterstroke of mission planning or the reason the bombs may not have finished their job. On June 22, 2025, 7 B-2 Spirit stealth bombers departed on a long-range strike mission into Iranian airspace. Each bomber carried 2 GBU-57 munitions. The total payload, 14 bombs. The mission designation was Operation Midnight Hammer. 12 of the 14 bombs targeted Fordow. 2 targeted the Natanz enrichment facility. At Fordow, the 12 bombs were not delivered against the mountain surface. They were delivered sequentially down 2 ventilation shafts. The shafts provided a pre-existing pathway into the interior of the structure, removing the first meters of penetration from the equation. General Kane said the first bomb removed the concrete cap covering the shaft opening. The main shaft was then exposed. Weapons 2, 3, 4, and 5 entered the open shaft, traveling downward at over 1,000 feet per second. Each detonated inside the mountain. The sequential delivery down the same shaft allowed each successive bomb to travel deeper than the previous one, using the cavity created by earlier detonations to extend its reach. This is the operational workaround for the penetration depth limit. Use multiple bombs in sequence down the same hole, each one going deeper into the damage created by its predecessor. The US Air Force and DTRA considered the mission successful. General Kane stated that the bombs achieved their intended effect. The Pentagon described the result as comprehensive destruction of the target. Then came the intelligence assessments. CNN reported on June 24, 2025 that an early Defense Intelligence Agency assessment based on a US Central Command battle damage assessment had reached different conclusions. Sources familiar with the assessment said Iran's stockpile of enriched uranium had not been destroyed. The centrifuges were assessed as largely intact. Intelligence indicated that enriched uranium had been moved out of the facilities before the strike. Iran had blocked the tunnel entrances with dirt and debris and capped the ventilation shafts with concrete prior to the raid. The early findings contradicted President Trump's claim that the strikes had obliterated Iran's nuclear enrichment facilities. The debate over what the bombs accomplished reveals a physical constraint. The Fordow facility's depth, 80 to 90 meters, exceeded what the GBU-57 could destroy in a single pass, even with the sequential shaft delivery method. A separate Iranian facility at Isfahan was struck with Tomahawk cruise missiles rather than bunker busters. The reason? Isfahan's lower levels are buried deeper than Fordow, and analysts assessed that the GBU-57 would not penetrate them. DTRA stated after the operation that it was waiting for comprehensive battle damage assessment data to determine how well the weapons performed. That data will inform improvements to the current design and guide the developments of follow-on systems. The agency referred to those future systems as very deep penetrating bunker busters, a designation that implies the current weapon is considered insufficient against the deepest targets. But operational limits are only part of the problem. The other part is how few of these weapons exist and what happens to Americans' deterrent when 14 of them are used in a single night. The publicly disclosed GBU-57 stockpile stood at around 20 weapons as of 2015, the most recent figure made public. Production has continued since. The Pentagon expanded manufacturing capability in 2024, but the current inventory is classified. Operation Midnight Hammer consumed 14 munitions in a single night. In February 2026, the Air Force finalized a sole source contract with Boeing exceeding $100 million to replenish the stockpile. Deliveries are not expected to begin until January 2028. The world's most powerful conventional weapon exists in quantities that fit inside a single warehouse. It can be depleted in a single mission. Replacing it requires years and 9 figures of investment. During the gap between use and replenishments, the capability does not exist. This is the design principle that receives the least attention and carries the largest strategic consequence. The GBU-57 is not a durable deterrent in the traditional sense. It's a single-use strategic asset available in very small numbers. Its existence as a substitute for nuclear weapons, a way to destroy deeply buried targets without crossing the nuclear threshold, depends on maintaining a stockpile large enough to be creditable. China observed Operation Midnight Hammer closely. Chinese military analysts assessed both the weapon's performance and its limits. China is believed to operate the world's most extensive underground military tunnel network. Chinese analysts noted the penetration depth constraints. The relevance to any future scenario involving Taiwan, where Chinese military infrastructure extends deep into mountain terrain, is explicit. Barnes Wallis proposed his earthquake bomb concept in 1941. He drew from the physics of seismic shock and the aerodynamics of spinning artillery shells. The core principle? A dense, narrow, hardened tube carries kinetic energy into a structure and detonates from the inside. Well, that remains unchanged across 8 decades of development. The GBU-57 MOP is the current endpoint of that lineage, but it's not the final bomb in development. DTRA is designing what comes after it. The arms race between the penetrator and the mountain continues, and the mountain is still winning against the deepest targets. The next generation of these weapons will need to go deeper. Whether they can go deep enough against facilities that adversaries know how to bury beyond the reach of any current design is the question that will shape conventional deterrence for the next decade. Hey, if you enjoyed this video, I'd love it if you could give it a like, subscribe, and check out this video here for more great military insight.